Good afternoon. Hello again. This is structural analysis made fun and easy. So this is example 2 of method of sections method of structural analysis for a plane frame. Well, it's actually a Paul frame, I suppose I would call it Paul frame. This is from University of Bolton School of Engineering, B.Eng on Civil Engineering. Semester 1 examination. This time, I've got another similar video, but this one is from 2019/2020, Engineering Mathematics and Structures module number CIE 5004. So this is statical determinancy, equations of equilibrium, method of sections for plane frame, Paul frame. Remembering that this one's got a pin joint in the middle, so usually you wouldn't be able to solve these videos, which I've explained in the other. Usually you wouldn't be able to solve these frames without stiffness method or flexibility method. This is example 2 of this type of problem. This is another good example. It's just to practice to apply the technique again, so you can see that it wasn't just a fluke that we passed. I have to be honest, I checked the answers, but that was definitely after I got the solution. I checked it on STAID, structural analysis program, so they were correct. I'm going to do some separate videos of that just to show you that it was correct. So this is, for this series, this is example 2. This is part 1 of 3, maybe it might be part 1 of 4. Please like the video, subscribe to the channel, and please donate if you can to let me make more videos like this. So let's get started on this one. So this is question 2 from 2019 to 2020, University of Bolton. The 3-pin frame shown in figure Q21 is pinned at supports A and F, with a third pin at D. The frame is subjected to a vertical point load of 50 kilonewtons at position C and a horizontal point load of 40 kilonewtons at position E. Okay, so let's just review the situation this time. So we got A, B, C, D, E, F. A, so it's 5 meters high till you get to support B, and then C, there's a 50 kilonewton vertical downwards point load at C. That's it from A to F, so span 6 meters. The position of the point load is at 3 meters. This one they've changed it because there's a pin support at D, and then we go back down 2.5 meters to E, and then another 2.5 meters to the pin joint at A. So there's 1, 2, 3 pin joints. Remembering also this is held. So there's a vertical reaction here, horizontal reaction here, horizontal reaction here, vertical reaction here. So that means we got 4 unknown reactions. Remember, so this frame is statically indeterminate normally, because we got 3 equations of equilibrium, but we got 4 support reactions. So normally we would have to use flexibility method or stiffness method to try and solve the frame. But as you'll see, or as you've seen already in the other series, that there's a good way to avoid a lot of complicated flexibility method or stiffness matrices, etc. So the calculate the question, just recapping the question. Also, it says part A, calculate the value of the support reactions at A and F. That's 5 marks. B is draw the actual force diagram, AFD, that's 4 marks. C is draw the shear force diagram, SFD, 4 marks. And D is draw the bending moment diagram, BMD, 6 marks. The going question says for B, C, and D, show all important values on the diagrams and produce accompanying calculations to show how these values have been derived. So I think I have done that, and I've done the calculations as well. So stay tuned for the solutions. I might break this up into 3 videos. It's just otherwise it gets a bit long, I guess, to watch it all like this. So as before, in example 1, now let's get into this. So for the exam technique, the first part it says find the support reactions. You get 5 marks for that. 5, and as I showed in the other videos, you get 36 minutes per question. There's 20 marks per question, so that's 1.8 marks, 1.8 minutes per mark. So on this question, you've got 9 minutes. So let's start with the fundamentals of structural analysis. Static determinacy or indeterminacy, as the case may be. Remember, we have 3 equations of equilibrium to use for plane frame analysis to determine the external reactions on the structure. In this case, we have 4 external reactions. Therefore, alas, for us life is not that simple. We cannot solve this structure using 3 equations because we have 4 reactions. The structure is statically indeterminate by 4 minus 3 equals 1 degree. Or can we, in some cases, we would need to use flexibility method or stiffness method. For more complex structures, we go to degrees of static indeterminacy. So, for example, if these were fixed, if A and F were fixed, then we'd have 6 degrees of indeterminacy. So then, even the method I use in this it would work because we have too many unknowns to solve it. So, however, in this case, I believe we have a get out of jail free card. Have you already spotted it? So, those people, hopefully, those people that watched the first series of the video, they know the answer now. You're going to use the taking moments about the hinge, use the method of sections, because D is a pin joint, and that means that there can be no moment at this position. Therefore, that gives us another. This gives us another way to resolve the structure. So, just in summary, I just need to zoom out a little bit because it's just a little bit. That's it. So, in summary, there's the frame. You got A, B, C, D, E. Oops, that should be F. Sorry. 5 meters high, 6 meters across, 50 kilonewton load at C. C is at 3 meters across the span. Oh yeah, so just I've highlighted the reactions. So horizontal reaction A is purple, RAH, RA, which some people call this HA, and then could also be called RAX, RAH, as in x-axis, RAH as in horizontal load, RAH, HA, RAX, so all the same thing. However you label it using one of them, this is horizontal reaction at A. The orange one, horizontal reaction at F. RAV, vertical reaction at V. RFV, vertical reaction at V. So, the sign convention again is in the x-axis, left to right positive. In the y-axis, up to bottom to top equals positive, and rotation about z-axis is mz equals to positive when it's anti-clockwise and positive and negative when it's clockwise. So there, it's all set. So the first, as you know, the first thing we have to do, we have to solve the we got to find we got to find the reaction. So we've got three equations we can use to find the equilibrium. This is also sometimes called free body diagram. So we got sum of vertical reactions, that must be zero. Sum of horizontal reactions, that must equal zero. And moments about, well, actually, moments about any point must equal zero. Obviously, if you don't know what the reactions are, and there's too many, there's more than three unknown reactions, then you can't solve it. But in theory, you could take moments about any point and it should be zero. Otherwise, the structure will not be in equilibrium, and the structure must be in equilibrium, otherwise it will be moving. Or it will be a mechanism. So let's start off with summation of vertical forces. RAV plus RFV minus 50 equals 0. So let's say RAV is upwards, RFV is upwards, minus 50 downwards. RAV plus RFV minus 50 equals 0. Let's call this equation 1. So rearrange this. RAV plus RFV equals 50. For horizontal equilibrium, RAH plus RFH minus 40 equals 0. So RAH plus RFH equals 40. So, oh yeah, I forgot to say at the beginning. Have you noticed something? In the other equation, in the other example, there were only horizontal forces. But in this one, we got vertical force, 50 kilonewtons downwards. So that makes a change from the last frame. There were only horizontal forces. So let's also use this to add to our experience of analysis. Let's see what happens now that we've got a vertical load downwards 50 kilonewtons, as well as this is a right to left force of 40 kilonewtons. So, now let's take moments about A. Therefore, let's take moments about A. So we got 50 times the lever arm 3. That's that one. That's minus because it's going clockwise about A. RA, obviously we take moments about A. RAH has no lever arms, so that's 0. RAV has no lever arms, that's 0. Then the horizontal load, right to left, the 40 kilonewton load times the lever arm for that is 2.5. So that is positive because it's going anti-clockwise about A. So 50 times 3 minus 50 times 3 plus 40 times 2.5, and then the final one, the lever arm for RFH is 0 because it's on the same axis as A, but the direction is on the same axis as A, horizontal, it's along the same line, but RFV equals 6 times, has a lever arm of 6, and the force is perpendicular to the axis. Therefore, if we take moments about RFV has a lever arm of 6 meters and it applies a moment, whereas RFH is parallel to the axis of A. Therefore, moments about A, as we just looked at, minus 50 times 3 plus 40 times 2.5 plus 6 times RVF equals 0. So rearrange this. Minus 150 plus 100 equals minus 6 times RVF. Remember in example 1 that we did uplift well. In this case, looks like the V load cancels that out because before we had tension in the second reaction. But on this one, it doesn't seem to be that. If we rearrange, we get 6 times RVF equals 50. RVF equals, RVF equals minus 50 over 6 equals 8.33333. Oh, so wait 1 second, I'll just check I've got that right. Minus 50 times 3 is 100, minus 150. 40 times 2.5, of course that's 100. So minus 150 plus 100, that's minus 50. Here it is. Minus 50, sorry, I've got it wrong there. Minus 50 equals minus 6 times RVF. Therefore, 6 times RVF equals 50. Therefore, RVF equals 50 over 6. So that's 48 plus 2 over 6. Therefore, RVF equals 8.33333 kilonewtons. Now we can go back into equation 1 because that was RAV plus RVF. RFV equals 50. Therefore, RAV equals 50 minus RFV, and RFV is 8.3333 kilonewtons. Therefore, RAV equals 50 minus 8.333 equals 41.6667. Oh, is it 6? Sorry, 66666. That's it. That's correct now. Isn't it? Yeah, I think so. It's 8 and 1/3, and RAV is 41 and 2/3. Okay then, so now we know the reactions. Oh yeah. We know, oh no, sorry, we don't know the reaction still. We don't know what RAH is exactly. We don't know what RFH is exactly. We just know that when you add them up, it's equal to 40. So these, the vertical reactions we found, the horizontal reactions, we know what the total of them is, but we don't know what they are individually. So what can we do? What are we going to do? Let us, so, and that is usually as far as we could get, or more than usual, because normally if we take moments about any other point, we would have too many unknowns, yeah. So what we could do now, we could take moments about B, but because RA is along the x-axis and they're both on the same line, we can't separate them into two. That's the other problem. The other problem is, we can't separate RAH from RVF. So there's actually another little problem because they've got the same lever arm. You can take